in this process, so mainly the heat transfer is important here in coke oven making process. So where is heat transfer? From the quenching procedures. So if we are supplying the excess of air, sorry, excess of water, so the quenching process, the rate of quenching or evaporation will be reduced. So that will cause the formation of a coke oven or coke is also reduced. So that's why you should control. Here is the rate limiting step is the quenching process. Similarly, another process like so when you once you finish the coke making, then you go for the blast furnace process. So in iron blast furnace process has evolved over many hundreds of years to become an efficient counter current exchanger of heat and counter current exchange of mass. So here is both heat and mass transfer taking place. Also fluid flow is also taking place. So here is main is the heat and mass transfer. The mass is transferred from the top to bottom, and heat is transferred from the bottom to top, like from the hot gas to the bubbles, solids. Okay, so this is so thus the iron oxides such as pellets and sinter together with coke and limestones are successively charged through the top of the furnace, and the charge slowly descends through the shaft and it's gradually heated by the hot ascending gases. So as the gas lower down, the furnace is richer in carbon monoxides, and therefore more reducing towards the iron pellets. So similarly, it is also the result of the main result of the this reduction process is the mass transfer of carbon monoxide, and also the hydrogen is present in the moisture to produce the reaction like so here is Fe2O3 O3, then carbon monoxide. So it is produced the, I think all of you know the reactions. So it produces Fe3O4 plus CO2, carbon dioxide. So these are the again the Fe3 and magnetite and reduced by the carbon monoxide, then it produces the FeO and also carbon dioxide. So the final deoxidation is accomplished down in the cohesive zone where high temperatures and highly reducing conditions result in reduction of waste or iron oxides to iron. So impurities such as silica, sulfur, alumina, and magnesium present in the original pellets associated with the lime and are removed as the molten slag. So the final reduction from the iron oxide takes place by a mass transfer mechanisms. So this is you can write the reaction like Fe plus carbon monoxide. So it generates the iron, pure iron plus carbon dioxide. So similarly, so here is again the carbon dioxide react with the coke, then it produces the carbon monoxide. So then similar way we can produce again the same process. So one is a direct reduction, another one is indirect reduction. Direct reduction means the waste is reduced directly, produced by the coke is known as a direct reduction, or indirect reduction when it is reduced by the carbon monoxide. So these two steps are generally involved in mass transfer case. So then you have to determine the carbon monoxide and carbon dioxide ratio. So it is also known as a solution loss reactions. So in solution reactions, what happens is a dissolution of coke by carbon dioxide. So this is generally known as a solution loss reactions. Although the purpose of coke is obviously to act as a reductant, it is also plays another critical role in that it behaves as a supporting pillar for overlying burden. So in the region below the cohesive zone, or otherwise known as sticky zone, everything else is in molten or melting conditions. So that means the molten air you see here, this is the case of this person is hot metals and there over is molten slags are there. So again, hot metal slag is we can drain out this directions also. In this direction, hot metal will you can pour out. So this is the case for blast furnace case. Then next slide, and we can so stoves. So blast furnace stoves generally, especially to generate the high temperature. To generate the high temperature required for the reduction of iron in the hearth region of the blast furnace, the incoming air is preheated prior to the combustion of the coke. So this, what is the here is, so again here is you come to the heat transfer case. So this is done by the passing the cold air blast over the hot preheated brickwork or check arc about 1500 degree Kelvin in the blast furnace stove. And since the cold air is gradually extract the stored heat, a separate heating process. So here is this is a cold air enter into the stoves, and then these are the check work. So you store the heats from the blast furnace gas. Then it is transfer the heat to the cold air, and then again exit at a hot blast to the blast furnace. So there are also this is affected by shutting of the cold air blast to the stove, opening of the gas valve, and this process is continuing, and the combustion enriching blast furnace of gases to bring the cold check work back up to the temperatures. Once again, this is an interesting heat transfer problem, and is posed concerning the optimum recycling time for a batch of stoves. This is you have to manage how much check work should be there and how much cold air should you supply to the uh, stove so that we can get the efficient heat transfer from the check work to the cold blast. So the next slide is steel making. So in steel making case, you see this is the view of steel making process. So in this case, what happens? Um, whatever the molten metal produced from the blast furnace, that is saturated with the carbon. And the next operation requires that this is the and other residual impurities like phosphorus, sulfurs, and also is removed. And the removal of impurities can be accomplished by the blowing high velocity supersonic jet of pure oxygen onto the hot metal. And dissolved carbon is oxidized and escaped as a carbon monoxide from the mouth of the vessels. So this process, and while other oxidized impurities are slashed off by addition of burnt lime. to compensate for the vast amount of heat liberated during the oxidation of these and other impurities like silicon manganese, about 30% of the total charge comprise the steel scrap as the coolant. So steel scraps are used in this process to reduce the what is the heat transfer or what is the amount of heat is generated inside the blast furnace. So this scrap coolant is required to avoid the temperature of the molten steel exceeding the 1923 kelvins. And so this is if you increase in the because of this reason, so it is also causing the unnecessary refractory reactions. And similarly, and the high here is this is not a single heat transfer process. Here is simultaneously three transport phenomena occurs. One is a mass transfer, heat transfer, also fluid transfer mechanism are involved. For example, mass transfer for breath of carbon to the scarp metal surface effectively dissolve the light section scraps even though bath temperatures are below a melting point of the scarp during the major portion of a blow. However, when the bath temperature exceeds the scarp melting temperature, this is around 1700 to 70 and 1800 to 10 Kelvin, normal thermal process involving the turbulent heat transfer, and the scarp which finally becomes assimilated into the molten bath. The typical mass transfer reaction in a basic oxygen furnace involve oxygen transfer to the exposed metal surface. So with the simultaneous transport of dissolved carbon from inside the liquid to gas and liquid interface, carbon is removed from the melt as a carbon monoxide. So here there is a different reactions also, and these are the silicon reacts with the oxygen, produce silicon dioxide and come to the slag. And manganese also is converted into manganese oxides, it is converted to the slags. And phosphorus also produce phosphorus oxides and come to the slags. So so here is one important thing. So it's a rate controlling step here. You are supplying the oxygen and so this oxygen when interact with the what is the carbon present in the melt, so it produces the heat. And so this is the rate limiting step here is oxygen. So this supply of oxygen is important. So that's why the steel making process is mainly they are focused on the supply of oxygens. So if you similarly high transfer also taking place from the your scarp, which is used as a coolant. So this is also mass transfer also that the impurities, what are the impurities present on the interface. So they are generate the slags. So this is also a phenomena like a mass transfer case. So in a basic oxygen furnace, so most of the reaction, transport phenomena, fluid flow, or momentum transporter is occurs simultaneously. Similarly, so this is your teaming is ingots and continuous casting process. So if you look at this process, so here is important is main thing is heat loss occur from the hot steel containing teaming ladle and furnace during the continuous casting operations. So these have to be minimized since the slight temperature difference can profoundly affect the quality of the slabs or billets that are produced. So heat is lost partially by conduction through the side and bottom walls of the ladle and partly as a result of a convection and a radiation from the top surface. So these latter loss are minimized by the use of a slag layer, and the 50 mm or more thick on the top of the steel, and the slag act as an effective thermal blanket. Additionally, alternatively, a ladle cover may be used also. So the solidification continuously cast slab or ingots is also an obvious example of heat transfer process. In this, the rate of metal solidification depends on the amount of heat extracted through the walls of a mold. And for instance, by the suitable adjustment of a cooling rates in the upper section of the static molds by use of hot tub compounds. So, here is you are generally using the slag layers. So these slag layers is behave like the one of the solid, one of the semi-solid or fluid layer, which is prevent the heat loss. So also enhance the solidification of the metal. So this is what is the here is the main concern is also a fluid flow also is taking place. So you should have to know what is the velocity of this mold, or what should be the viscosity of this slab. Then you can determine the proper, you can maintain the proper solidification in the ingots or in continuous casting slabs. So this is the main points or main this is a heat transfer main one of the transport mechanism. So these are the different transport phenomena you will find in our metallurgical process like integrated steel plants. Also you can find in our rolling mills also, hot rolling mills also. So this is hot rolling mill. You can see here also this is there is a simultaneous also heat transfer also taking place also. So how can you maintain the heat transfer rate of transfer from the solid hot slabs so that we can easily reduce the slab? So this is an important consideration for the hot rolling mill process. So these are the different different metallurgical process occur in our metallurgical process. Apart from this, other processes are also there. So, like melting, like our mineral processing, also leaching process. So these are all metallurgical processes are involved in the transport phenomena. So then you come to the basic fundamental of this phenomena. You will see here what should be the velocity profile of this slag, or what should be the shear strength of the shear force distribution in the slab. So you have what should be the thickness of the slab, so that you can prevent the heat transfer, heat loss. So these are the different. So it will take more time to understand the things. So then you come to the mechanism momentum transport. So what happens actually in how we can derive, how can solve these problems, industrial problems, by using our fundamental or mathematical derivations. So before I go into this topic, you should there is many books are available in the maybe the website or maybe our different publishers. So here is the description of the transport phenomena is different in different considerations on it based on their concept. So basically, in meteorological transport phenomena, it is totally different from the transport phenomena dealing in any other processes, other branches of like civil engineering or chemical engineering, somewhat more or less similar. Other mechanical engineering also. Mechanical engineering parts of like rolling or manufacturing process also similar in. So actually in civil engineering they are considering this moment fluid flow. So they are all considering microscopic phenomena. Microscopic phenomena. So just you have supplying the water through the pipe, what is the rate of flow, what is the power required to supply the water. So this is you can calculate. But in meteorological process, what happens whenever you supply the things, fluid flow taking place, there is so many things. For example, there is a mixing of alloying elements. So there is also transport of heat also simultaneously. So these are the main thing is the mixing of the alloying elements. That means mass transfer, like a segregation. So in segregation, what happens? Simultaneously, are heat transfer, mass transfer. If the mass transfer is there is if it is not in a particular fashion, so you will get the segregation in the mold or in castings. So then, so these are the main concern. We are dealing with the micro. That's why we are dealing with the microscopic phenomena. So the microscope is a totally different phenomena because we are considering the microscopic levels. What happens inside the fluids. So what is the flow or the velocity profile inside the system, or what is the or a shear stress profile? What is we are saying? This is a momentum profile. Okay. So that's why there is a different consideration of different laws, where fundamental laws apply to each and every flow independently of nature of the fluid under considerations. So these laws are listed are in different books, like there most of the laws are the laws of conservation of mass, or you can say continuity equations. Newton's second law of motion, or also you can know for the momentum theorem. And the first law of thermodynamics, you know the energy equations. So these are the basic equations. So can you utilize these equations, you can solve our problems, most of the problems. And then by your mathematical, mainly differential derivations. So here is the so this is the case of a same one of the casting ingot. Okay. So in casting ingot, you see the tundis, you are supplying the liquid metal to this mold. So here is we have to find out which transport mechanism is going on here, or what is the mechanism about transport or momentum transport. So here is two references there. How can solve the problems? Two references. Yeah, this is your nozzles. This is your jet. So you are considering the jet. This is the jet portions. Okay. So here is the upper portions are you are considering here. This is the liquid stage, and they enter into the jet and then come to the mold. This is so here is two reference. One is a Langerian frame of reference, another is a Earlian frame of reference. So basically, the transport phenomena we are using the Earlian frame of reference. So what is this frame of reference? Now, what is the difference between these two approaches? So this is mainly one is mainly based on the position in the field is identified. Difference main of these two approach is only position of the field is identified. For example, in Hungarian approach, the physical variables are described for a particular element of fluid as it traverses the flow. So as the flow is going on, so you should sit on the flow. So for example, you should be follow along the flow of the fluids. So this is the familiar approach for particle and rigid body dynamics. So the coordinate axis here is x, y, z are the coordinates of the element of the fluid as such, and the function of time. The coordinates x, y, z are therefore independent variables in the Langevin form. The coordinates are dependent because whenever the fluid is going, you are following the fluids. So that means here this is the dependent on the dependent variables coordinate axis. Always different from the different positions. So this is similar. The fluid element is identified by its position. So here is fluid element. We are considering here is identify its position in the field at some arbitrary time. So for example, time is equal to t is equal to 0. So then this is you can write this equation, the functional form by v is equal to like v is equal to function of v is the function of a b c and t. Okay. So here the coordinate are A, B, C refer to the initial position of the fluid elements. So this is the Langevin frame of reference. But when you consider the Erlang approach, so this approach actually what happens now, it is seldom used in fluid mechanics. So it is not in everywhere it is used. Somewhere it is used, or there is the value of a particular fluid variable at fixed point, the flow, rather than the value of a fluid variable experienced by an element of a fluid along its trajectory. Okay, so but in earlier approach gives the value of a fluid variable at a given point. So this is at a given point and at a given time. In functional form, we can write so V is equal to V is a function of x, y, z. X, y, z. Okay. So here is x, y, z, and t are all independent variables. For a particular point, you can write like x1, xy, x1, y1, z1, or t1. Similarly, also you can write at or x2, y2, t2. So this gives the velocity of the fluid at that location at a time t1 or t2. So this is here the case. You see here you are considering one time t1 for the Langevin or another time is t2 for the Langevin frame of reference. But in case of earlier reference, only you are considering the small portions of the fluids. So what is the mass enters into the system and leaves the system? What is the heat transfer enters into the system and mass transfer heat transfer leaves the systems. So this is the we are using. This is the case, or in case of a Langerian, you have to follow what are the between the 2 points. One is a time t1 and time t2. So this is the two difference of frame of reference. Especially we are using for our solution for easy solutions. So we are using earlier frame of references to solve our problems. So then you come to the. So this is how you can solve the problems or how can find the momentum. So using the Newton's law of Newton's second law of motion. So you know the rate of momentum changes. So you are considering the axis. This is the z axis, and this is the considering a radial axis R. So here is the F is sum of the force is equal to F is equal to mass into accelerations. So here is again you differentiate this convert into differential equation. So you will get the with time we will get the mass into velocity divided by into del t by del t. So this is atmospheric pressure force acting normally to the two horizontal surface of the volume elements. So the force of acceleration is equal to mass into acceleration also. So in case of you are considering the earlier volume elements, so this is generally is known as control volume approach. The control volume approach, so you have to find the acceleration, you know, dv del v by dt. Or again you have by partial integration, then you can convert it by del v by del z into del z by del t. So this is become the velocity into del v by del z. And which is then integrated from the position 0 to h. This is the height. And v is also v0 to v. So v0 and velocity at the center and velocity at the near the wall of the tube or jet. So then you have to find the FCS is equal to half mv square. So this is v square minus v0 square. So then when you substitute, you will get the rho GH. As this rho GH is equal to, you can again convert it to the, this is the half a rho v r square minus a half rho v0 square. So from these equations, the equations you rearrange, so you will get the momentum equations. So this is the rate of mass transfer, rate of change of mass into the velocity. So also you will get the, this is the momentum of the systems. So the next slide. So here is the, this is actually the simplest way to explain the Newton's law of viscosity. So this because viscosity is important whenever we're talking about the momentum transport. This viscosity also we are considering like this is the mainly whenever we're talking about viscosity, there is one question arises in our mind. So this is the resistance force. So resistance to the flow of the fluids. So this is also already you know there are different types of fluids like Newton fluid, non-Newton fluids, and so these fluids are most of the fluid you are considering in transport phenomena. So these are the Newton fluids. whether there are slags or there are molten metals, or you are considering all are Newton fluids. So this then you can this is the case to find out the viscosity of the fluids by simply using this expression. So then you can determine the Newton's law of viscosity. So here is the example on the fluid content between the two plates. Fluid content between two plates. One is the upper plate and the lower plate. So the lower plate is stationary and the upper plate is moving with a force and above the fluid. So the fluid, this two plates are separated by distance y. So a force of constant magnitude F, when you apply it to the upper plate in the x directions, the later it begins to accelerate in the x directions, the upper plate. The movement of the upper plate set up a shear stress between the plate and the fluid, so which opposes the motion of the plate. So here is a stress or the interface between the fluid and the plate. So here is shear stress developed. So this shear stress opposes the motion of the fluid. That means direction of the shear stress in this directions, acting in this direction. So this is known as y x. Tau x. So this is so as long as it is going on, so that is a steady state reach. So when at this stage, what happens now? The applied force F is balanced by the shear force. The applied force balanced by the shear force, and in which state the upper plate has a constant velocity also. So the upper plate also maintain the velocity v, and at the steady state, the Newton found that the velocity v is proportional to the applied force F and to the spacing y, and inversely proportional to the surface area of a plate. So this is, you can write here, v is directly proportional to the F and y and inversely proportional to the area. So then you can rearrange it so by like that. So you can F by A and directly proportionally V by Y. So you can write the V F by A is the shear stress at the interface between the upper plate and the fluid. And so this shear stress is a tau is directly proportional to the del V x by del Y. Also you can write differential form also. Here you can say the shear stress is proportional to the velocity gradient in the fluid. So here is the proportionality constant eta is known as the viscosity of the fluid. So you can write this equation tau yx is equal to minus eta del Vx by del y. So this is the Newton's law of viscosity, and Newton's law of viscosity also states that the shear stress between the adjacent fluid layers is proportional to the negative value of the velocity gradient between the two layers. Also this shear stress also you can is defined as also the rate of momentum transfer per unit area. This is also the shear stress is also, you can express it as the rate of momentum transfer per unit area between the two adjacent layers of a fluid is proportional to the negative value of the velocity gradient between them. So here is, you see how we are express the shear stress to the rate of transport of momentum per unit area. So here this is the case. So if you look at the distribution velocity profile, you can see here the velocity is directly proportional with the, this is the linear relationship with the distance. Okay. So as you move, it is so this is, that's why the sorry. Okay. Sorry. So here is the fluid. The what is the fluid here you are using here? This is it should be with the Newton's law, or this is otherwise it is not. But this equation will not vary. And the second thing is, so if you multiply or you divide it, the fluid density, then you can obtain the nu. So this is known as momentum flux. Sorry, this is known as kinematic viscosity. Or also you can express this tau ix into tau yx into minus mu by del v x by del y. So this is that the tau is the main is the you can define this is ability to transport the momentum. More is the nu, more is that ability to transport of the momentum. So the negative sign here indicates as the velocity dv by dx is positive. The direction of a momentum transport is from the region of a higher velocity to lower velocity. So that's why it is a rate of momentum transport is a negative quantity. So momentum is a, that's why also the momentum is transport from the down the velocity gradient. So that means your viscous molecular momentum or a viscous momentum transport from the down the velocity gradient from the higher surface to lower, sorry, upper plate to the lower plate. So here is a maximum momentum here and minimum momentum here. Because the shear stress is here minimum, here is maximum at the stationary. So this is so as the rate of transport of momentum in y direction due to the fluid motion in x directions. So this is equal to the shear stress denoted by the tau yx, denoted by the tau yx. So this tau yx indicates the rate of transport of momentum in the y directions due to the fluid motion in x directions. So that is a this is the to prove the Newton's law of viscosities. So if you want to calculate using the control volume approach, so then you want to so you then you come to this control volume approach. So here you can see. So what is the microscopic phenomenon? What is macroscopic phenomena? Here you see you have to calculate the same term here. These two phenomena here is. So here you can also calculate the what is average flow rate, but here you can calculate the actually the velocity of the particle. So here is generally in metallurgical process we are considering the fluid system or continuum or it consists of atoms and molecules. Okay. So each we are analyze each atoms and molecules to find out the what is the velocity profile, what is the shear stress profile. So accordingly, we have to determine the flow rate or mass flow rate or your force, what are the force acting over the system. So these are the we'll consider in the case of our when we consider the control volume approach. So here is different parameters in metallurgical process array systems. So here the input parameters are the process variables like temperature, pressure, flow rate, and composition. And the processes like temperature, pressure, and output variable, the product variable, temperature, pressure, flow rate, also compositions. So these are the different terms. So here is used here to how can you express the then these are the different. Okay, here. So the momentum balance equation here. So how can to balance the momentum? What is using the Newton's law of viscosity. So the one simple way you can you know the balance equations very well. So here is you can use and simple control volume approach. So the volume is V of this particular system, and then there are velocity, area, viscosities are A1, A2, are the input values and output values. So here is you can you see the word form of the momentum balance equation is rate of change of momentum is equal to the net rate of outflow of momentum plus the force acting on the control volume. So these are the we can express here in this way. So here is one you can see here so momentum rate of change of momentum dp by dt is equal to rho uva. So this is the converting momentum. This is the converting momentum of the fluid. Then you come to this. This is the pressure force. This is the drag force. This is the external force acting over the systems. So especially in most of the metallurgical process, we are considering in the transport phenomena the forces like gravitational force or other force. What is the mechanical force acting over the system, or here you see the different. How can you balance the momentum so that you can solve the problems? And this is the simple process, a simple balance equation. This is the so here we already discussed here. So this is the one another approach to find out the momentum balance using this control volume approach. So before going to solve the moment balance equations, so you should know the first is this the fluids properties, whether it is a Newton fluid, non-Newton fluid, whether it is a flow is a laminar or turbulent. So whether it is a steady or unsteady, whether it is a fully developed or incombustible fluids. So these are the conditions you have to assumptions you have to consider. Then you come to solve the problem. How easy to solve the problems. So this is all the same case. We are considering the upper portion of the fluid is moving, upper portion of the plate is moving, a lower portion is stationary. So you have to find out in which direction the momentum transport taking place, so that we can easily balance the momentum equations. So here is already see here under the steady state conditions, the rate of momentum balance equation is rate of momentum in minus rate of momentum out plus sum of the force acting on the systems. So here is another force also we can pressure force also we can consider here. So here is you see, so here this is the system, the fluid content between the two plates, and we are considering a control volumes. So this control volume is depend upon your reference, shape of the reference, whether it is, for example, this is a parallel plate, so that's why considering a rectangular manner. So if it is a cylindrical, so your control volume should be in cylindrical, so that it is easy to solve the problems. So here is you consider, so the volume here is this is the coordinate of control volumes. So one is a x, y, and y and z, and another coordinate is this point would be delta x, delta y, delta z, del. So here too the size of the control volume is, so we can see here if this point is x, then it will be x plus delta x. Similarly, this is also, and similarly, so here the volume of this control volume is equal to delta x, delta y, and delta z. So this is the smallest, infinite small volume we are considering that flow systems. So then you have to find out in which direction the viscous momentum, transport of viscous momentum taking place, or in which direction the convective momentum. So there are two types of momentum: convective momentum and viscous momentum. So convective momentum generally occurs along the fluid flow. In which direction fluid flowing, same direction in convective momentum is the direction of flow of the convective momentum. And similarly, already we discussed the viscous momentum. The viscous momentum generally it is transport from the along the velocity gradient. It's from the higher velocity to lower velocity. So this direction is direction of momentum direction. So for example, in this case, we can consider the viscous momentum is transport from the top to bottom, and convective momentum is transport from the this same to. So when you consider to the this control volume approach, so then you can assign here. You see, so this is coordinate system to, and in which direction the fluid flow, and in which direction the viscous momentum. So here is different. You assign here this the one, this is the B, and this is, so here convective momentum entering XY phase, sorry, YZ phase. So this is the YZ phase through which the convective momentum enter into the control volume. And similarly, it is living through the YZ phase at B. Those are the distance x plus delta y x. So then you can write this one is a rho v square into x plus x. Or the first one you can write also, this is the rho v square x. That means actually here is rho v x. This is the rate of momentum into along the velocity direction vx, like that. So that's why it is a rho v square, vx square. So similarly, the viscous momentum enters from the top to bottom. So the phase is here is XZ phase through which it enters the control volumes and leaves the control volume these directions. So then you can write this viscous momentum is very simply. This is we can write this is tau Ix. Because velocity in x directions, the momentum in y directions. Okay. So similarly, we can write this one as viscous momentum entering through the space where this is the point. This is that means this is the y plus delta y. And another one, viscous leaves at the position tau Ix at y. So this delta x delta y is this the area here. This is the delta x delta z is the is the area. So similarly here is delta y delta z the area of the control room of this space area. So then you can here you see how you convert the rate of converting momentum expressed in rho v square into area. So this is the simple use expression for the rate of momentum or converting momentums. So then you balance the balance equation. What equation you see here? Rate at which converting momentum enters into the control volume minus rate at which converting momentum leaves the control volume plus rate at which viscous momentum enters the control volume minus rate at which viscous momentum leaves the control volume. So as it enters the steady state condition, so it is equal to 0. So there is no accumulation in the system. So you can rewrite these equations. This is the converting momentum, enter difference between the converting momentum, and this is the area. This is the viscous momentum is equal to 0. So here you can you have to note down. So here is in steady state flow condition, Vx is a function of only y here. Vx is the only function of y. So it is does not vary with either x or time. So that's why the term is Vx at x or Vx at x plus delta x. So both are equal. That means this term is tend to be 0. But when you consider a microscopic phenomena, so it will be not 0. So that is something is. So this is the difference between macro and micro. So we are considering always a microscopic phenomena here in transport phenomena or moment phenomena. Okay. Any question? Okay. So thus the converting momentum enters and leaves the control volume at the same rate. So that's why it is a 10 to 0. So the only remaining term is viscous momentum. So this viscous momentum you can rewrite here divided by the volume, control volume. So you can rewrite this form. Okay. So this again you can use the limiting conditions. You know the differential equation and limit. So you can delta y tend to 0. So this will give the delta yx by del y is equal to 0. Then if you integrate these equations, so you will get the tau yx a constant is C1. So then you have to find out the boundary conditions to evaluate the C1. And so this C1, so you can substitute this equation also from the Newton's law of viscosity. So in Newton's law of viscosity, tau yx is equal to minus eta del vx by del y. So then again you have to equating this equation. So you'll find the velocity profile. Under the integration, we will get the velocity profiles. So this is the equation. We will get another constant sheet. So you have to evaluate these two constants using the boundary conditions. So here is boundary conditions like so when the velocity is 0, at what? At y is equal to 0. That means the lower portion, lower plate. Upper plate is moving with the velocity v and lower plate is stationary. So this is the y is equal to n is 0. So where is the velocity v? Then y is equal to capital Y. That is just some distance already I told. So this is the y. So then you apply the boundary condition to this equation 3. So you will get the reduced to this equation and c is equal to 0 when you put in this boundary condition. So then you get the v is equal to minus c1 by eta into y, or also you can evaluate the c1. So when you c1 this is equal to with the equation 3, you will get the vx velocity is equal to v by y, capital Y into the function of y. So here you can see the velocity vx is proportional to the velocity gradient. Okay, and it is independent of viscosity of the fluid. Also a linear function of y. So similarly, also you can substitute in equation 2, we will get the tau shear stress is equal to v by y and into eta. So here is also same. This is the tau ix is independent of y. What is the proportional to the viscosity of fluids? Okay. So this equation also you can graphically you can also see here also. Okay, sorry. Graphical representation. Sorry. Already I think put okay here. Okay, here. These two equations, so you can see here are and its velocity profile here. Sorry, this is the velocity profile. You not say. Okay. So this is the case of you have to find out using the momentum equation. Similarly, you can. So this is the simple case. So similarly, you go for the if you derive the Navier-Stokes equations. So this is actually the momentum balance equation in 3-dimensional. So here you only consider the 2-dimensional. Okay. When you consider this 3-dimensional equation, so easily you can apply the different situations, response systems to solve the problems. Okay. So thank you very much. So may I request any questions on your side?
Yes. Good afternoon, sir.
Okay, welcome.
Well, I am Sudhir Pradhan, Assistant Professor, Department of Civil Engineering.
Sure, welcome.
Sir, have a nice lecture. And actually, first few slides, actually, it is beyond my department, actually, civil engineering.
Because it is the topic is like that, that's why.
Okay. No problem. But last few slides are that is related to viscosity. That is purely our civil engineering department.
Yeah.
And I also learned from the metallurgical processing because somehow or somewhere it is related to civil engineering. Not directly, but indirectly it is related to civil engineering.
Sure.
And my question is that actually, very simple question. Sir, actually, viscosity, in our civil engineering perspective, viscosity is the most vital points, and I think this is the most contradictory point in civil engineering actually. In civil engineering, when we are designing or working on polymer actually, basically. Sir, first tell me whether viscosity only depend upon the temperature or it will depend upon also other factor. What is the main criteria actually first? Only temperature is the main concern or other points are also for viscosity?
But in metrological consideration, we are considering the also temperature or composition also. Okay. That's why I would. Okay.
That's okay, sir. In civil engineering also, means for polymer compound, it will depend upon the temperature. That is okay.
Okay.
It is okay, sir. Is there for metallurgy or any other also, any other material? Is it depend upon the any other factor?
Any other factor? It is temperature. Actually, I think.
No, because sir, we have seen actually when we are modifying the polymer as a sometimes what happened if temperature increasing, basically the rule tells viscosity
decreases.
Then vice versa. But when we are modifying means adding some sulfur or any other type of chemical, if the temperature increasing, viscosity also increasing. That is the point actually. So
okay, that means you should consider the composition points. Man, what is the polymer compositions? Okay.
Okay. Sir, another thing, from laboratory point of view, it's okay that you have told that direction of convecting momentum or viscous momentum or shear stress. That is okay in a laboratory point of view. But when we are going to field or practical field, sir, because there are many factors that.
That's why there is some assumption. You should have. You should also analyze some critical point also. So it is along with the assumptions, then you can solve the problem. Or this is not only single one equation is just like momentum. So simultaneously you have to consider the three momentum transport equations. Sorry, transport phenomena like mass, heat, and fluid. Then you can solve the problems. Whenever you go, there is not alone one mechanism is acting. Many simultaneously three mechanisms are play.
Okay. Means we have to consider different points. Then at last you will take some assumptions. Then we'll conclude that is okay. By consider. Okay, sir. Thank you, sir, for very valuable.
Welcome.
Okay, sir. Thank you, sir.
Thank you.
Thank you.
Thank you very much, sir, for giving us more information on transport and metallurgical processes and its various mechanisms and transport processes. Thank you. Any more questions? Delegates now can ask. Thank you. So now we have come to the end of today's program. I hope you have enjoyed this day and gathered new information in transport phenomena and metallurgical processes. I must thank you all for your kind cooperation and I look forward to meeting you all here tomorrow. Thank you.